Okay, so this is a single phase, split phase induction motor here, and I'm going to do a little demonstration here. This motor, I'm going to run at about 30 volts just for safety reasons. Don't try this at home because it does deal with line voltage, and this is just a demonstration. So running on 30 volts, you can see it draws about 1.26 amps. This induction motor has a rated RPM of 1725, but it is tied to line frequency. So the line frequency, the cycles per second with a 2-pole motor would translate to 1800 RPM. But for a single phase induction motor, it has to run lower, just a little bit lower than the line frequency, because you have to have this thing called slip in order to have current induced on the what is effectively windings in the armature, so that the armature can develop a magnetic field to chase and repel the stator. So it has to have a little bit of slip, and this is about a 4% 4 to 5% slip here. If you don't have that slip, you have no current induced in the armature, and then you have no work done by the motor. So if the actual armature was running at 1800 RPM, then it would have no effect on the stator. And what happens is, if you're to slow this down, the more slip there is, the more the armature, more current is flowing through the armature windings. And when that happens, the mutual inductance between that and the stator causes the stator's natural counter EMF, which makes it an inductor. It offsets that and causes the stator to draw more current, and as I'll demonstrate here. You can see it's drawing about 1.3 amps. Now if I come over here and slow this down, you can see that the current increases. Right now it's about 1.6 amps when I slow it down. That's because the slip increases and the relative speed between the stator and the armature is greater. The relative speed, that means that the magnetic lines are more quickly cutting the windings in the armature, which are just single turn windings. When you're more quickly cutting them, the current flowing through them is related to the speed in which those magnetic lines are cutting it. So that relative speed is higher between the armature and the stator when you slow this down. Now, if I lock this rotor, the effect is much more profound. Of course, we're going through a start-in main winding here at the same time, so I'll acknowledge that. But if we go ahead and lock this rotor, you'll see how much current it draws. Now we're at over 9.5 amps. That's because the stator is still going at its rated speed. It's still oscillating at 1800 cycles per minute. 1800 equated to 1800 RPM. It's still oscillating at the same rate, but now the relative speed is, the slip is 100%. You have the relative speed of 1800 RPM. So the armature is actually inducing there's a lot of current being induced in the armature, and that mutual inductance between the armature and the stator is causing the natural EMF, counter EMF of the stator to be highly offset, and making the stator look much less like an inductor, and causes the impedance of the stator to drastically drop, causing the current of the stator to drastically increase. That's it for this video. I hope you found it interesting and informative. If so, please give it a thumbs up and subscribe to this channel.